Hello, everyone. Thanks for joining and welcome to our webinar. It's called the Trillion Row Cloud DB Speed Test. And my name is Yukti. I will be your moderator for this webinar. So one of my main jobs here at SingleStore is to organize weekly AI webinars. We organize maybe two. You will see three webinars coming this for this month mostly. So we also demonstrate different data and AI use cases in our webinars, new tools and technologies, thanks to our amazing team here at SingleStore that help us to drive these webinars. We also post about these webinars on our channel. So if any of these topics are interesting to you, feel free to connect with me or follow SingleStore to stay on top of the loop. I'll also like to hear your feedbacks or any ideas on topics that you would like to see in future sessions. So feel free to connect and drop a message to anyone on the team on LinkedIn. So speaking of future sessions, can we please go to the next slide? We've got amazing, informative new webinar sessions that are coming up. So as you can see on your screen, we have how to talk to your SQL data with function calling, which is tomorrow. And it will be presented by Madhukar, who is an amazing content putter out there. So if you're interested for a very educational session and to learn something new, this is the webinar that you will go to. You can scan the QR code and it will directly take you to the landing page. And on September 4th, sorry, that's September 10th. I'm really sorry that the date is wrong. The webinar will be called Intro to Vectors. And this is a very beginner-friendly topic and will also cater to a little intermediate level audience. So this will be presented by Akmal, and I hope to see you all there. Akmal is a very regular speaker at our webinars. And on September 9th, we have Augment Your DB to speed up your and scale your SaaS apps. So if you're already using Mongo, this is a great chance to enhance your vector DB, and we and just to see that how we can help there. So this is the future plan as of now. So if any of these topics are interesting to you, RSVP right now, and I hope to see you all there. Coming back to today's topic, you're welcome to participate in the discussion throughout the session using the Zoom Q&A button. It is present at the bottom of your console. We have an internal mission statement to try to answer 100% of the audience questions online. So even if that means following up with folks afterwards via email, if you have a specific use case, just make sure that you have logged into Zoom with your name and email address, because we will not be answering any anonymous questions. Moving on, I would like to announce our raffle for today. So if anyone who tries out SingleStore will be entered to win either branded new AirPods or Meta's new Ray-Ban LLM smart glasses. This is absolutely your choice. Simply click the link that's present on your screen. I will be putting everything in the chat as well for easy access. And just log in. That you may know that SingleStore has had a free trial offer for many years, but in the past few weeks, we have also announced a new free share tier, which we will talk about a bit later today. I highly encourage you to load in your data and create a workspace just to have a more hands-on experience during this webinar. So just feel free to try SingleStore today. And moving on, we should announce our amazing speaker today. So we have Eric Hansen, who is the Director of Product Management here at SingleStore and has done amazing webinars with us before. So very happy to have you here, Eric. And we also have Akmal, who is here to answer any SingleStore related questions. Meanwhile, in the chat, and he's an expert and is going to speak at our future sessions as well. And so, all right, so take it away, Eric. The floor is now yours.
Hey, thank you. Hello, everybody. Again, I'm Eric Hansen, Director of Product Management here at SingleStore, responsible for several technology areas, including query processing, which I'm going to talk about today. And so the goal today is to show you how we can process over 1 trillion rows per second in one query on SingleStore Helios, which is our cloud service. So first, let's talk a little bit about SingleStore. So why should you choose SingleStore? Why consider using SingleStore? SingleStore has really fast ingest, low latency query, and can support very high concurrency. So this combination makes it great for many different types of applications. SingleStore is fantastic for all three of transactions, analytics, and search. Now, today's talk is all about analytics. I'm not really going to talk about transactions and search today. This is about how we get fast interactive response time for large aggregate queries. So to recap a little bit about SingleStore, some of you may be very familiar with SingleStore, some of you may be new to it. but let me tell you what SingleStore is. So it's a SQL database management system. It supports fast scale. It's extremely fast, and it's fast because we support scale out, compiling of queries to machine code, in-memory data representation, and vectorized query execution, not to be confused with vector search. This is a form of column store query execution that gets very high performance by storing data from columns and vectors. So we have an in-memory row store and a disk-based column store. Again, we support transactions, analytics, and search. Today, I'm going to focus on the column store. So the scale-out architecture of SingleStore allows us to spread a database across multiple computing nodes and allow all of those nodes to work in parallel to solve a query. So this is a really simplified diagram of a SingleStore workspace with one aggregator and 4 leaves. And there's a client application. The client application always connects to the aggregator and submits SQL statements. And the aggregator splits up the work across the leaf nodes, and your data will be horizontally partitioned across those leaf nodes. So there'll be an even spread of data across the nodes. So let's talk about why interactive response time for queries is important. So there's been psychological research done on responsiveness in computer systems, and this is what they learned. Something about 1/10 of a second feels instantaneous. You really can't perceive how long it's taking if it takes 1/10 of a second or less. Up to about 1/4 of a second, it more or less feels instantaneous. And then response time of 1 second feels very quick, and it allows the user to maintain their flow of thought. They don't stop and think about, why is this taking a long time? They just go from one step to the next in their process of exploring information. And then something that takes up to about 10 seconds can still maintain the user's attention. They don't get bored and start thinking of other things or other tasks that they want to do. So there's a URL that links to an article about the psychology of response time in computer systems. So SingleStore can drive great user satisfaction with instantaneous or in-the-flow responses. And it can help you maintain your user's attention. So if you use the well-structured column store and design your tables right, your sort and shard keys correctly, you have the big enough hardware, even on tremendously huge data sets, you can get interactive response time and give that really terrific experience for the end user to keep their attention. So here's a little quote that is from an early psychologist way back in 1890 that I think is interesting. So I'm going to read it for you. Stimulation is the indispensable requisite for pleasure in an experience, and the feeling of bare time is the least stimulating experience we can have. So what does that mean, bare time? It means just waiting for something to happen. So people don't like to wait. SingleStore can help you avoid having your end users have to wait. So before I get into the details of the demo and how I achieved 1 trillion rows per second response time for a query, I want to talk to you about my personal story experiencing query performance. So, over the last couple of decades, tremendous progress has been made in getting fast query response time. I remember back in 2006, I was using a legacy row store oriented, disk oriented database with a B-tree access method. And I'm not going to name names, but I ran a query on 100 million rows, and it took 2 minutes on a moderately large server. Fast forward to 2012, same database with a column store. A query on 1 billion rows took 2 seconds. And fast forward 6 more years, we were able to demonstrate on with a self-hosted installation on state-of-the-art at the time Skylake servers in an Intel lab, doing a query on 58 billion rows in 0.05 seconds. So this was achieved 1 trillion rows per second barely, just got over 1 trillion rows per second. But what I'm going to talk about now, 6 years later, is on our Helios cloud service. You can come up with and create a cluster and get almost twice as fast performance as we got 6 years ago on stock hardware that's available in AWS. We set it up, we manage it for you. You can start it up, shut it down whenever you want. So there's no need to buy and install your own hardware in your own lab to get this level of performance. So it just makes it accessible to just order at least an order of magnitude more customers that can achieve this level of performance by having it available in the cloud. It just makes it so much easier. So let's talk a little bit more about the need for speed. Users come to, they become used to fast response timing and they expect it once they've seen it. So you want to be able to produce state-of-the-art response time for your, and through your applications for your end users. And so satisfaction increases as response time decreases, as you would expect. Again, delays over 50 to 150 milliseconds are perceptible in real-time applications. And the median human reaction time, not necessarily perception time, but reaction time is about 250 milliseconds. Like if you say, look out, to get a person to pay attention to you takes about 250 milliseconds, or to react to a ball that you throw to them, that kind of thing. So, minute-long response times are boring. People lose attention. 10 seconds, maybe you can keep their attention, but they're not going to be thrilled. 1 second, they're going to be thrilled. Fraction of a second, incredibly thrilled. So let's figure out how to get to that fraction of a second response time for large queries. Some more subtleties about response time are that high variance can bother users, like less than a quarter of the mean or greater than 2 times the mean can bother users. So it can help to give a message if you're going to have high variance. Unintuitively, I would say, unexpectedly fast results can make users apprehensive until they get used to it. Then they'll be okay with it. So we've seen with SingleStore, when we start to demonstrate it to people and they run a query and it takes like sub-second time and they're used to that kind of query taking minutes on other systems that they've used, they don't believe it. They're like, something's wrong. But then they get used to it and get to realize that SingleStore can produce that kind of response time, and then they're okay with it. Fast response time can lead to more input errors because people don't think so hard before they run something, but that's a minor problem compared to this benefit, which is that fast response time can make users interact and explore more with their information system. And that creates a lot of business value because the business user is going to get more interesting information from their information system and be able to take action on that information to do a better job with their business. All right. Before I get to the demo, and I promise you there will be a cool demo towards the end, let's talk a little bit about SingleStore query execution technology and why it is so fast, how we can get this interactive response time. So I already talked about scale out, and I showed you that diagram with aggregator node and multiple leaf nodes showing how we spread the data across multiple servers. So we have scale out. We compile queries to machine code, and that produces that really helps with response time. So if you run the same query multiple times, we don't have to compile it every time, and compiling the query can take a while. So by using compiled queries and a plan cache where you run the same query multiple times, it doesn't have to compile after the first time. That improves response time. And we have an in-memory row store and a disk-based column store. Both of those can give you fast response time. We also support vectorized execution, which I'll say a little bit more about. And we use Intel AVX2's SIMD, or single instruction multiple data instructions, to get really fast response time. So I mentioned that we compile queries to machine code. For a compiled query on a SingleStore row store, which is really good for transactional workloads, but can also do a tremendous job for analytics. So we can get about 24 million rows per second per core processing rate. Compare that to 1 or 2 million rows per second per core on an interpreted database management system that's using a disk-based access method like Postgres, MySQL, SQL Server, Oracle, etc. So, we're at least an order of magnitude faster than those legacy B-tree-based row-oriented access methods. And this is when data is in our row store format, which is highly suitable for transactional applications, yet still we get order of magnitude faster analytics on that data for great real-time analytics. So today I'm going to give you a demo that uses only the column store. It's not using the row store. So column store tables are our default table type. They're disk-based, so you can store a very large amount of data, much larger than the available RAM on your servers. Data is stored in typically 1 million row chunks called segments. And each column within those segments is stored separately. And you only read the columns that you touch. So if you have a query with several columns and you're only touching, like, say, 2 of the columns, you only have to read those 2 columns. You don't have to even read the other columns from disk. And so that can give a better response time. And the data is highly compressed. There's also minimum and maximum values per column, per segment. So if you have a filter, like a range filter, you can skip entire segments in that case. We also support something called vectorized query execution, or vectorization. And basically, we process data in our column store queries in 4,000 row chunks. And so for each chunk that we read, we read a vector for each column into an in-memory array. And we process these column, that vector of 4,000 elements for each array can be processed in a very tight loop of C++ code. SingleStore is implemented in C++ for high performance. And so you can apply filters and local group by operations and joins to these 4,000 row vectors super fast with very tight loop of code. And so when you fetch more data during a column store scan, it fetches 4,000 row chunks at a time. And that allows us to amortize the fetch next overhead, giving us really fast performance. So typical performance when we're processing data with this vectorized method with C++, even when we're not using SIMD instructions, is a few 100 million rows per second per core, like 200-300 million rows per second per core. So this is instrumental to interactive response time. But SingleStore even uses something that can be even faster in some cases, which is single instruction, multiple data instructions to process data in its native format. So we use Intel AVX2. This supports 256-bit registers. We pack multiple values per register. So we use special SIMD instructions that operate on these wide registers. A standard computing register is 64 bits on an Intel chip, these AVX2 registers hold 4 times more information. And they have special instructions to do arithmetic, logical instructions, load and store, and so forth. And it allows multiple operations in one instruction. So this is a really simple one that does 4 adds in a single instruction. And this is illustrated here. But you can put even more data in a SIMD register. Like you may, if you have 1 byte per value, you could have 32 packed into an AVX2 register. So we use AVX2 and SIMD to do what we call operations on encoded data in SingleStore. So encoded data is data that is in its compressed format. So for example, if you use compression, you can say each dictionary key is only 2 bits. You can pack like 128 rows worth of data into a single one of those 256-bit registers. So we can do filter and group by operations directly on compressed data in SingleStore. And in some cases, we can process greater than 3 billion rows per second per core using this approach. So again, this is applied before the vectorization for local group by. And I'm going to do a group by aggregate query today that uses these operations on encoded data to demo a trillion rows per second plus performance. So here's a sort of an illustration of operations on encoded data. So suppose you have rows, like 6 rows of data next to each other, then they have a certain column stores a string red, and then blue, then green, then red again, then blue. So there's 3 distinct values there. So to represent 3 distinct values, it only takes 2 bits per value. So suppose green is 00, red is 01, blue is 10. For 6 rows of data, we can pack that into only 12 bits. So a query like this, like select color and count star from T group by color, can use operations on encoded data on this data representation to do incredibly fast processing. And I'm going to show an example of that. So now I'm about to get to the demo. The demo setup is as follows. So I have an S128 workspace. So this is 128 SingleStore units, and there's 8 vCPUs or logical cores per unit. So that's 1024 cores. And this is located in AWS US West 2 region. I've created a database with 1024 partitions, and flexible parallelism in this case I turned off. So flexible parallelism is on by default, and it splits your physical partitions into several logical subpartitions and allows multiple threads to operate on each subpartition concurrently. So it's a great default. In this case, to eke out the absolute most performance, I did disable flexible parallelism because there's a little skew in my data. I generated some random data, and the data skew caused me to not get quite peak performance. But flexible parallelism is a great default and can get close to the performance I'm showing you today. So within a factor of 2 on this very data, and if the data wasn't skewed, it would be almost on par without flexible parallelism. So the table size I'm going to show you is 57.7 billion rows, and it's data on sort of mock stock trading data on a stock exchange with 2,921 companies. So the table schema that I'm going to use to run a query is this mock trade table. So each row has a unique ID number, and then there's a stock symbol, and then the number of shares traded and the share price and the trade time. So that's the data that makes up this table. And I have a seed table which has those 2,900 companies that I talked about. And I use that to feed into a random data generator to generate so 58 billion distinct rows. And I'm sorting and sharding by the stock symbol so that I can do local group by operations. So local group by allows me to do a fast group by locally on each leaf node. And then the intermediate group by results are then forwarded to the aggregator node, and a final group by is performed up there to run the query I'm going to show you. So now let me get to my demo. All right. So I'm going to share a different screen here. Okay. Hang on. Okay, everybody see my screen?
Eric, any way to make the text a little bit bigger, please?
Yeah, let's see what I can do here.
How's
that?
It should be an option from the browser, I think, isn't it? Yeah, that's great. Thank you very much. Thank you,
Okay.
sir.
All right. So my workspace, it's called Workspace 128. It's got it's an S128 with 1024 vCPUs. The database I'm using is called Trades3. So I got a couple tables in there. I got company and trade. So trade is the one with the 58 billion rows of data. So let me demonstrate that to you. So I did a count star query on trade. You see that it says 57.7 billion rows. So here's an example of the kind of data that's in there. So every column, every node, every row has a unique ID, stock symbol, some number of shares that were traded, the share price it was traded at, and the trade time. So I've got, all data for 2,900 different companies in there. This is the schema again: ID, stock symbol, shares, share price, and trade time. So here's the query that I want to show you and prove to you that this is running at a trillion rows per second scan rate or more. So I just ran that query. Did you see how it came back almost instantaneously? And here are the 10 rows that it retrieved. So you see there's some big companies here, which is what you'd expect, that the larger companies would have more trades. And so I'm going to go through, I wrote some stored procedure code and an anonymous code block to get the runtime. So it says it ran in 54 milliseconds, but that includes the round trip time from my browser to the cloud service and back again, which is a substantial fraction of the entire time. So I need to figure out how long it really took without that round trip to the browser. So what I've got here is I've written a stored procedure called profile query. And let's read through this. So it takes a number n, which is number of times to run the query. And then I've got two variables, this TS1 and TS2, which is going to be the start and end time of the query. So I can subtract the TS2 minus TS1 to get the runtime. And then Q here is that query. This is grouping by stock symbol and doing a total count, and then order by the count and descending order and limit 10. So when we declare so this array here is going to be used to hold the result of the query. So here's the body of the stored procedure. So we get the start time, TS1, which is now 6, which is the current time with microsecond precision. And then we're going to do this n times. We run collect on Q. So that's going to run the query Q, this query, and get the result and assign it into that array. And so we don't use the result, but we do get it that many times, n times. And then we get the completion time. And now we return the seconds per query, which is, we do timestamp diff microsecond, TS1, TS2, that gives us the microseconds per query, divide by 1,000,000, and then divide by the number of times we ran the query, and that gives us the seconds per query. So let's run that and see how many seconds it takes per query on average to run this. So 0.032 seconds, so 32 milliseconds per query to run a 58 billion row full scan. It's going to touch every row in order to accomplish that query. So now let's see how many rows per second it took. So this is an anonymous code block. So this is a very popular programmability feature that is part of our extensibility capability. Basically, an anonymous code block, it's a begin end block where you can declare some local variables. Then you have a begin end block which can have any statements inside of it. And this has the same kind of capabilities that you can use in a stored procedure body, but it's anonymous. It doesn't have to declare a new object in order to use it. So we got this double. This is going to be the runtime per query. So we can say X equals profile query. And so this is actually a way to call a stored procedure, then take the return value and assign it into a variable. So it doesn't use the call or echo statement, but it actually does call this stored procedure. A lot of people don't know that you can do this, but this is a very convenient way to get the output value from a query, from a stored procedure, and put it in a variable in a store proc or in a non-code block. And now I'm going to echo out the rows per second, which is the total rows in the table divided by the number of seconds it took to run this query on average. So let's run this. So it says 1.8 trillion rows per second. Wow. So we just demonstrated that on a S128, we can process a query at nearly 2 trillion rows per second. That's just a phenomenal amount of throughput that is enabled by scale out, shared nothing architecture, compilation of queries, and vectorized execution, as well as operations on encoded data. So this is running on SingleStore 8.7, although this will work on prior versions, this kind of demo. Let's take a look at the explain plan for this query. So again, this is the query that we ran repeatedly. So I can go up here and say, well, I'm going to profile a query to get the profile plan. So let's look at the scan operator. So at the very bottom here, we have the column store scan. If I click on it, this shows the metrics for the column store scan. And so the one you want to look for is this one, segments. Well, there's a couple of them. One is segments filter on encoded data. That's this one. It says 0 right here. So it didn't apply any filters because this query doesn't have any filters. So it didn't filter on encoded data. But this one right here says segments encoded group by. So we did encoded group by on 57,267 segments. And that's roughly the number of segments in the entire table. So this shows us that we got the encoded group by to kick in, and that was critical to us being able to get this nearly 2 trillion rows per second processing rate. So if you want to know if encoded operations kicked in, you can look at your explain plan, look at the column store scan operator, and look for these segments encoded group by, as well as segments filter encoded data, and see if they're non-zero. That means that operations on encoded data kicked in. So operations on encoded data works best for group bys on low cardinality grouping keys. So that means, less than like a couple thousand total elements. For very high cardinality group by keys, it's not going to kick in. But in this case, we only had 2,900 total group by possibilities. So operations on encoded data was able to kick in. Right. Nope. All right, I'm going to share a different screen now. So 1.8 trillion rows per second. So just to recap, SingleStore is great for analytics that maintain the user's flow of thought and attention, because we're able to get this really fast interactive response time. And this is enabled through scale out, compilation of queries to machine code, as well as a plan cache that caches query plans for previously executed queries. So you don't have to include the compile time and the wait time to run the query. And then vectorization, as well as SIMD operations on encoded, and SIMD instruction usage, as well as operations on encoded data. And we got 1.8 trillion rows per second scan rate on stock hardware from AWS. This is the standard hardware that anyone will get when they create a S128 workspace. And so the cool thing about this is that on our cloud, you get easy deployment. You don't have to worry about buying hardware, setting up a lab. You can do this, and you can run it over the long haul if you want, or if you just want to do a short-term project, you can deploy a cluster and run it for a few hours and shut it down. You can pause and resume your workspaces, scale them up, scale them down very easily on SingleStore Helios. So try it free today. Here's the URL for our cloud free trial. And I want to thank you, and I'll be happy to take any questions at this point.
Thank you, Eric. That was so cool. So, attendees, that if you have any questions, we are now going to take up any questions live. So, Akmal has done a great job answering your questions. So, if you have any questions, this is the time to ask, and feel free to keep them coming in. Akmal, is there any question that caught your eye?
Yeah, Yuktia, did you mention that we don't take anonymous questions? Did you say that?
Yes.
I wasn't listening.
Yes.
But there's an anonymous
I
question.
see one.
One anonymous question. And I think, Eric, this was referring to, if I go back to your slide, where you mentioned your personal story experiencing query performance. So an anonymous attendee asked, what type of query was that? I don't know if you can recall from...
That was a group by aggregate query. They were all like single table group by aggregates.
Okay, great. I think that answers that. There's a couple of questions there from Muhammad Rafiq. So he's got several actually.
By the way, hang on, hold on 1 second. So yeah, they were all group by aggregate, full scan type queries without filters. So to really just measure like the sort of worst case query performance for scan with group by aggregate.
Okay. Awesome. Thank you. Couple of questions. I'm sure you can see that yourself there, the Q&A, Eric, but there's Muhammad Rafiq has got several questions in there. I think a couple of them are fairly long as well. So he seems to know his stuff there. I'll leave you to peruse those and
Let's
because I
see.
think they refer specifically to your demo.
Let me see if I can find the questions.
Yeah, should I read the first one
Wow.
out? Or can you see those?
I see Team SingleStore to everybody, but I don't. Maybe I'm not looking
Okay,
at the
let
place.
me read out the questions then, Eric. So
Okay.
for the first one, he says, do these row chunks in brackets or something like row group maintain metadata like min max or just for the entire 1 million segment, as if we have min max for smaller segments like 40 or 50K? Can we eliminate a lot of scan right, as 1 million seems to be a big number? I hope you can get the gist of that.
Yeah, I got that. So now today we just have the min-max metadata for entire segments. Now you can turn your segment size down. Like if you want to be able to eliminate more data with the min-max, you could say turn your segment size down to like 100,000. But right now we have the min-max metadata on a per segment basis. It's something we're considering for the future to maybe have an option to have sub-segment min-max to do more skipping, but right now it's per segment.
Okay. And I think he's got a couple of follow-up questions, which I'll quickly read again. The next one that Mohammed asks is, does maintaining smaller segments and their meta cause any overhead?
Smaller segments and their metadata, and maintaining that does cause a little bit of overhead. So the segment metadata is kept in RAM. So like if you turn the segment size way down, you might, it's not healthy really. I'd like going below like 50,000. I would seriously question trying to do something like that. And so there's a little per segment overhead and in the scan operation, we have to open up each segment to get ready to scan the data inside of it. And that's going to have a tiny amount of overhead per segment.
Yeah. Okay. Great. One more here from Mohammed, and then we'll get on to some other ones. So this is another long one. So bear with me a moment, Eric. So it says, do these row chunks? Oh, sorry. I think he's already asked that. Hang on. Does maintain? Yeah, the third part. What will happen if we do join on such large table? How will it affect performance?
So if we do a join, so this table is a single table query. A join is going to be a little more work, so it'll be not as fast as this, but we can do hash joins to small dimension tables to a large fact table, and do that with the hash join will use operations on encoded data if there's a low cardinality join column. So you can get extremely fast like hash join pipelines with small dimension tables that it's not going to be as good as what I showed you, but it'll be very good.
Okay, great. Question from Ryan. He says, I didn't see an index on the date column in your trades table. How would performance be affected with, in quotes, typical indexes in place?
If you sorted by date instead of, so I didn't use an index on date in column store. You don't use indexes for ranges. You use a sort key. So I could have put a sort key on date instead of on a sort key on the stock symbol, and it still would have gotten operations on encoded data, but it wouldn't have been quite as good as this.
Okay.
But it would have allowed things like date range filters. Like I could do a group by aggregate only on stuff that was less than a month old, that kind of thing. And it would have not required a full scan in that case. So for your specific application, if you have date range filters, that may, dominate your consideration when coming up with your physical database design. You probably want to sort on date and not sort on that the group by key.
Okay, great. Two questions here from Peter, Eric. So Peter's first question is, segments in blog, is almost the same question mark. I'm assuming that was referring to something that you were showing in terms of the, when you were actually doing your demo, showing the metrics and the numbers on the right-hand side. I don't know if you recall that.
I don't know if I understand the question. I think maybe we need clarification on that.
Yeah, Peter, if you could just perhaps expand on that a bit, okay? Just post an update on that, and we'll get that to Eric. And then the second question was roughly how large is each row, and how much data actually needed to be touched to satisfy the query?
So the it only had to touch it didn't have to touch any columns except for the stock symbol column. It only had to touch that one column. It had to touch every row, however, and it was going to be using dictionary encoding with like a couple 3 bits per row. So not much data.
Okay. And overall, roughly,
it did have to spend time on every single row.
Right.
But it was an incredibly small amount of time per row because it was using like chunks of like 64 or 128 rows at a time with SIMD in order to do this.
Gotcha.
Interestingly enough, so our operations on encoded data technology is patented, and we actually, the way you do a group by operation like I described is a hash group by. You normally keep the hash table in RAM. Our operations on encoded data, when it's doing the initial local group by at the segment level, it doesn't even use RAM to keep the hash table. It keeps it in the SIMD register set. So that's one of the reasons this can be so fast.
Great.
So the SIMD registers, like RAM is fast, cache is fast, registers are even faster. So it's using the SIMD registers like RAM in order to get it to go faster.
Great. Okay, so got a follow-up there from Peter. So he's asking if 5% new data was being inserted during the query, how different might the results be?
Well, the query runs so fast that I don't think that's even possible. Like but suppose you were inserting new data during the query. The new data would go into the in-memory row store segment. Okay, so it wouldn't be in column store format. So the time it would take to process the column store data would be the same, but the time it takes to process the in-memory row store segment would be something like 24 million rows per second per core, which is going to be, it might be couple 3 billion rows per second per core for the column store formatted data. So if you just have a tiny amount, like a fraction of a percent of the data is in the in-memory row store format, you'd have to do the math based on the processing rate to see how much impact that would have. But it could still be interactive like this. It's not going to be as fast, but it should still be, if there's just a few thousand rows in the in-memory row store segment, this time would be about the same. If there's millions, then it might be noticeably different based on the scan rate that I quoted.
Yeah. Great. Got a question here from Robert, Eric. He says, so about how much did that query cost? Question mark. I mean, you're trying to do a bit of arithmetic there with your anonymous blocks.
The query took 32 milliseconds.
32 milliseconds.
So 0.03 seconds.
Gotcha. Yeah, and I could see you were doing a bit of arithmetic there with your bits of code and an anonymous block there. So that's awesome. Okay, let's have a look. Let's see if we got anything else. Ahmed got a general question. Any SDKs API? So, I mean, we do have support for multiple languages, JDBC, ODBC, Python, Java, you name it, they can work with that. And I think one of my colleagues, Yaroslav, is actually working on a dedicated client for SingleStore. So much like you have like the CLI client for MySQL, for example. And he's also got it's one of these JavaScript clients built as well. So we do have various tooling available. And we can send you the link for that as well. I don't know if you want to chime in there. Anything you want to add onto that, Eric?
Yeah, you're absolutely right. So you can use this. This is just SQL query execution. So when SQL queries come in from any kind of API, they'll get similar performance.
Great. Let's just see what else we can find. So yeah, Robert, just clarifying that point there. So on the cost, I meant money cost. How much money cost? Okay, so that would be based upon your what was it, 128, and each of those
Yeah,
will
I
burn a
can't
certain amount of
remember.
credits.
Yeah, you have to look up our price schedule
Yeah,
and
yeah.
in
Yeah,
order
Robert,
to
we
see
can send you
that.
that. So, yeah, so we
Yeah.
can find the link for that and send and follow up and send you that. So there is information on our website. It actually gives you a detailed breakdown and shows you. So when you sign up, I mean, if you haven't got an account, as Eric was saying, you sign up today with a cloud trial link. Basically, you get about $600 of credits. And you get the free tier. So these are great ways. It's kind of entry level, great way to get started. Just get your feet wet, try it out, and test it out for yourself. Small scale projects, but if you want to scale up and use it in anger for big projects, obviously I understand. The cost is something that will be important to you. So we can certainly follow up with that and send the appropriate details. That's great. Let's have a look. Yeah, got a question here for forgive me if I mispronounce the name. Divyanshu. Yukti, I don't know if you want to correctly pronounce that, but asking a
No,
question.
it's right. Ganshu is
Okay,
right.
all right. So my apologies. I'm terrible at names, I'm afraid. So is this replacement for what MongoDB in application development, or I didn't understand what it was? Okay, I can take that. Eric, if I can just so essentially we have a product called SingleStore Kai, which is a MongoDB compatible layer. So it effectively gives you the ability to use SingleStore as though it's like MongoDB. You can move your code across. And in fact, we've covered many webinars and we have many notebooks. We have many blog articles, demos demonstrating this capability. In fact, if I can just quickly mention, and I'll hand over to Eric because I'm sure he's got some comments as well. Just recently, for example, I looked on MongoDB's GitHub repo. They presented a webinar just very recently. I took their notebook, I brought it over to the SingleStore environment in terms of our portal, our Jupyter kind of like notebook environment. And with just a handful of very small code changes, because there's some nice features that we have that give us the ability to put in like a small URL versus that long string that you have to type in for the MongoDB sort of cluster and the server address and so on. And I got that code working fully. And it, I didn't do a performance comparison. There was no head-to-head comparison. And that's fairly typical. So my boss, Maduka, did another event just recently, a webinar, I think it was within the last couple of weeks, where he was very much demonstrating kind of a Node.js front end and how he was able to take some Mongo code and literally he was able to transfer it and move it across to SingleStore, and SingleStore, happily using the same sort of technology. And so I'll give it over to Eric. Eric may have some thoughts on this as well.
Yeah, and so the neat thing about our Mongo Kai capability is that we take Mongo. So we take your documents. If you create a document collection through the Kai API, and underneath we store that as a table with a JSON column, and we store JSON documents and we shred them into a column store format internally. So you can do queries on through Kai using the MongoDB notation that does the equivalent of a group by aggregate they call them aggregation pipelines in the Mongo terminology. And they're turned internally into just regular SQL group by aggregate queries. And they can run incredibly fast, like 1,000 times faster than Mongo. We've got, blogs and demonstrations that show that. So it depends on your query, depends on the data, but it's easy to get dramatic performance improvements for Mongo aggregation pipelines using Kai. And it can use this operations on encoded data and scale out and compilation, that all the performance features that I talked about today are available through Kai.
Yeah. And Jason, who's been really driving the Kai initiative at SingleStore, I know he's done blog post and some demos where we did kind of analytical queries on Mongo versus SingleStore. And SingleStore, some of the queries up to nearly 1,000 times faster for analytics. Okay, so there's some great stuff that we have, and again, we've got references, so I can pass those on to Yukti. So for the follow-up email that she'll send out, we can include those references for you as well. Okay, Yukti, I think we're almost at the top of the hour, or nearly half past the hour where you are in India. So perhaps you want to do your prize draw and maybe. We seem to have got most of the questions there. I think anything else that's not answered, we will follow up, as Yukti mentioned at the beginning.
All right, thanks so much. Can you please share your screen again with the follow-up webinars? Because in case that anyone joined late, I will, let me just put it again in the chat as well, because apparently it disappears for anyone that joins in a bit late. So they can't see the chat. So I'll put it again for anyone that joined late. We have amazing sessions that are coming up, and they will be soon be on your screen as well. Tomorrow, we are going to present how to talk to your SQL data with function calling. You can scan the QR code and it will directly take you to the landing page and you can RSVP. On September 9th, we have Augment Your DB to scale up and speed your data and your SaaS app. So please join us. And on September 10th, we are presenting Intro to Vectors, and Akmal is going to present that one. He's a very regular speaker at our webinars. So it will be a very hands-on, which is going to cater to all beginners and intermediate people. So sign up, and I hope to see you all there. Moving forward, we also have, I earlier announced a raffle that was there for this particular event. We will be announcing a winner by the end of the day. So if you have still not registered, the link is there in the chat. Just try out SingleStore notebooks, and I will be sending out the code to Eric's notebook in the follow-up email. So if you want, you can watch the recording and follow up in real time and try to do similar stuff that Eric was doing on SingleStore. And you can do that by utilizing the free shed here, right? I guess that will allow people, right, Akmal?
Yes, I mean, certainly you could start, but you wouldn't get to, I think, Eric's level of the quantity of data. I think it will exceed the limits of what we will allow.
Yeah, but I mean, like you can try with a sample data.
Oh, yeah,
set.
yeah. I mean, definitely, you can test the code out at small scale. Yeah, yeah.
Yeah, you can, and using that, you can be eligible for the raffle as well. So
yeah,
thank you for
definitely.
joining, everyone, and I hope to see you all again. Eric, thanks so much for the webinar you did for us today. We are actually planning to put out content using the recording for this webinar. So I'm very excited for that, and we will make a reel out of it. So stay tuned for that as well. And thanks everyone for joining. Have a great rest of the day. Bye-bye.